Institute of Indian Foundrymen Chennai Chapter. I welcome all fellow foundrymen for this wonderful webinar. The great Rajmohan is going to present the knowledge sharing on furnace lining. Normally, any foundryman used to face the lining life or the lining material or the premature failure of furnaces. It is a common phenomenon where Rajmohan will come and support at any point of time. Even I used to call him in the midnight to support me in many occasions. So likewise, whatever the knowledge he has got on in line with the furnace lining and refractory, the new type of refractories need to be used for furnace lining. Those things he is going to explain in his presentation. I request all the foundrymen to attend the fully, and Rajmohan will be in a position to give any answer for all the queries at the end of the program. So, welcome you once again for this webinar. Now, I request Vignesh to introduce Rajmohan to the forum so that Rajmohan can take their on. Thank you.
Thank you, Raman sir. Gentlemen, it gives me immense pleasure introducing our speaker for the day today. Mr. Rajmohan Mathiazhagan is a qualified BTech chemical engineer from the Adiman Engineering College, Hosur, and he is also an MTech ceramic technology from Alagappa College of Technology, Anna University, Guindy. I think he's a gold medalist in MTech ceramics. And Rajmohan started his career with Allied Refractory Products as a sales engineer in the year 2008. And in 2012, he was promoted as regional manager for South India, and he's currently heading the sales of Allied India at the moment. He holds a total of 14 plus years of experience with Allied. Earlier to Allied, he was at QMI Super Refractories as project trainee and as a production engineer at SVS Chemicals. He has visited various countries like USA, Germany, Tanzania, Sri Lanka, and Thailand for various projects, both like for installation as well as for GIFA and sales conferences, etc. Apart from his profession, he is an athlete who has won medals in 400 meters, 400 meter hurdles, 110 meter hurdles, and 20-kilometer race walking. And he also plays hockey as a forward, and also he plays tennis regularly in recent days. So with that, the floor is yours, Raj. Take us through the refractory technology, please. Thank you.
Thank you, Vignesh. Thank you, Raman sir, for a wonderful introduction. So I'd like to thank the IIF Chennai Chapter for initiating and organizing such webinar for the benefit of a fellow foundrymen. And thanks for giving me an opportunity to be a part of it. The topic for today is not a new one, and many of us here would have already heard the same from me or many other refractory players in the market. The idea for doing it is to keep everyone refreshed, and if we note any process deviation in our operation, this will put ourselves back to the track for following the best practices to attain more lining life and to reduce the cost involved towards the refractories. Now I'll get into my presentation. Today I'll be covering grout, spout, top cap, care for the lining tools, and common lining problems, and the way to overcome the problems. First, I'll start with grouts. When we talk about grouts, actually, technology has changed a lot, and everyone here are moving to new technology for better refractory performances. We changed from boric acid silica linings to boron oxide silica linings. For steel melting applications, from MgO lining, we converted to spinel and neutral linings, like ladles, from sand to castables. But still, there's a less attention given to grouts. People still use the same traditional conventional castables. Again, I'm not saying that these are bad products. These are not meant for these application. So what a grout material should contain? It should have excellent properties, traveling properties. the grain sizing should be like 2 mm and finer. It should be more volume stable, and it should take up less water, and it should be easy for dry out. So if you can see this slide, actually you can see about a rough grout versus a smooth grout. Refractories are designed actually with some particular grain structures to get an optimum output, like strength. By sheaving the larger grains in a traditional conventional castable which we are using, you are disturbing the strength of the product, and also wasting the material by consuming only a portion while paying for the whole. All these can be avoided by a proper selection of grout. As I said, actually, the grout plays a vital role in your lining performance. So when it comes to the dry out of grout, drying of grout is one important step when you try to maximize the refractory lining life. We recommend to do the dry out either by flame or power. Burner is most preferable. Heating through a halogen lamp is not recommended because commonly everyone follows this. So we don't recommend drying of grout with a halogen bulb. So we recommend to follow the cycle recommended by the refractory supplier with the help of a thermocouple. This will help to remove the complete moisture from the system in a slow phase. The dry out cycle can be designed based upon the size of the furnace and the amount of grout material is consumed. Normal recommendation is to raise the temperature till 300 degrees Celsius. So you can see a small graph in the screen, which is a common thing, but we can adjust this. We can frame this based upon your furnace size and the material has been consumed. So these are some pictures which shows how we suggest actually how normally a grout has to be dried out with the filament heaters. So in this slide, actually, this slide talks about the dry out of a grout through a burner system. As you see in the slide, place the former upside down by placing a brick at the bottom. So the former will be standing over the bricks. Place the burner in such a way that the flame is inside the former and the hot air flows through the bottom and moves upward between the grout and the form. Place a thermocouple through which you can detect the temperature and we can control the temperature. So this is a slide actually which shows normally we recommend using a moisture meter. This is a moisture meter which we can use to detect the moisture level in the grout. Once the moisture is below 10, the furnace is ready for lining. Some people go ahead with the GLD values also, which is again a good thing. You can record the values before the dry out cycle is started and after the cycle has been done to correlate the values and to proceed with the lining. So here I'm talking about, I'm not sure how many people of here actually would have known about these type of grouting systems. Normally, the grout is done by troweling application, but we have grouts which can be pourable or casted. So this is a pourable grout, or we can call it as it can be called as a casting of grout. Here, as you see in the slide, we set the form as per the lining thickness or grout thickness suggested by the OEM, and we engage actually a self-flowing castable for doing this operation. We also introduce a small vibration to the form. So you can see these numbers, those are forms which can be removed actually after the setting. So in this form, we normally give a small amount of vibration, and this vibration helps the castable to flow smoothly and to avoid any voids. Normally, this has been done in large capacity crucibles, but we can do the same for the small capacity crucibles also. This gives a very smooth finish and has a better strength compared to a trowelable castables. So now I'm moving on to spout. So we always recommend spout to be done prior to the working lining. This will help the main lining to expand and contract with no hindrance. This will reduce the maintenance in that area and avoid metal penetration happening below the spouts. So as I said earlier, if the spout is done after the working lining, when the expansion and contraction of the main working lining happens, there will be a crack between the spout and the main working lining, which paves a way for the metal to penetrate. So always do the spout first. So this is what I'm talking about. If you see the second picture, the arrow here, indicates actually the crack over here and leads to a metal penetration, because when the lining expands and contracts, the lining pushes the spout up, while contracting, the spout stays still on the top, creating a gap over here, and the metal might penetrate here. This is a common scenario which we have seen in most of the foundries. So we recommend to do the spout first and then do the working lining. So you can see when we do the spout first and the working lining second, actually the maintenance is very minimum. We always recommend a plastic refractories for the spouts, which has 2% moisture. So prior to the working lining, we need to remove this moisture and allow the refractory to shrink. So we recommend to use an external burner, and depending upon the quantity of the refractory being used, the dry out of the spout timing can be scheduled between 2 to 4 hours. Make sure you make vent holes for the moisture to escape easily. So this is a new thing which is an upcoming trend actually. It's precast spouts. So the spouts are precasted based upon your dimensions of the spout dimensions, and it's easy to install. It has long running campaigns, and the downtime is very less. So the way to install is actually you put a plastic refractory in the bottom where I'm showing with the cursor, and then you set the precast tap hole, precast spout, and then on the side again you can fill it with the plastics to hold the spout actually in place. So coming to top cap is one area where we have seen widely in the market least importance is given till date. People normally go with sodium silicate mixed either with the ramming mass or with the sand actually, and they make the top caps generally, where high maintenance is required and a lot of unsafe operations are happening actually because metal leaks around that area. So we talk to the customers in such a way that actually the attention to be given in this area also. So when we are talking about top cap refractories, it can be either dry, wet, or plastics. For silica, we engage all the above said, like plastics or castables or dry versions. This is one type actually silica based, which is we increase the bond percentage. For an example, if you're using 0.8 or 1% boron oxide for the main working lining, the top caps can be done with 1.5% BO or 1.8% BO, so that this product sinters a little bit at low temperature and gets the strength. This is one more few silica based top cap materials with extra bond. We normally recommend a few silica based actually on the top to have a good volume stability. With the extra bond means actually that under low temperature it sinters very fast and it gains the strength. And even if you have any mechanical abuse, it can be resistant actually towards the mechanical abuse. And again, as I said in the before, it's ideally suitable for silica linings. So this is one thing where you can see a little bit of needles actually in this ramming mass. These are needles. These are SS needles actually. So this is again a fused silica, which has a good volume stability, completely dry, bonds actually very good with the working lining, which is silica. Minimizes the top cap separation. All these dry versions, whatever I'm talking about, minimizes the separation between the main working lining and the top cap material. Normally, we recommend this product wherever there's more damages to the top cap area. This SS fibers will act as needles, will act as a thing actually to give more strength, and it reduces the amount of cracking and damages happening in that area by giving more strength. So this is plastic top caps. You can see top cap made out of plastics, and these are castable top caps. We can engage actually, as I said, we can engage castables also as a top cap material. When it comes to care during top cap repair, whenever actually you try to repair, don't remove the complete lining on the top. Always try to keep the original lining as a backup, as shown in this picture, in the first picture. So don't do like this. Don't remove the complete refractory. Partially remove the hot face and then set a form and then fill it either with a dry version or a castable version or go with the plastics. But always let us have the original lining as a backup. And also, one more thing is try to do the cut actually in the refractory like inclined actually like this. Don't do it on a right angle cut. So you should always have the cold face on the upper side and hot face a little bit on the lower side, and then do the patching. Because in case if any metal penetration is going to happen, the metal will have to travel up and then go towards the coil. So it will take some time. By the time actually it happens, actually we can have a GLT detection and we can shut down the furnace. So don't do a right angle cut like this. So coming to the summary of selecting a right top cap refractory, I always suggest actually my customers to go with a dry top cap refractory, since actually it will give a complete monolithic lining with no seam line separation. What we mean by seam line separation is, for an example, you have a dry ramming mass at the bottom, and then you're trying to put a castable on the top or a plastic on the top. These are two different products, two different product lines. And the merging will not always be proper. And always you will be having a small seam line separation, which will be having a way for the metal to penetrate inside. So we always recommend dry top cap, like what I talked about, like fused silica based or normal silica based with high % boron oxide, or fused silica based actually with stainless steel fibers. And we ask our customers to avoid sodium silicate top caps, since it does not have good strength and requires a lot of repairs in the complete campaign. As shown in the picture, whenever you're going with the dry top caps, make a transition layer. So take one bag of the main working material and one bag of top cap material, mix it, and put one layer where the blue has been indicated. That's a transition layer. And once that has been done, then you can go with the complete top cap material on the top. So in case if you want to, if you have a high mechanical abuse, we can go with the ultra low moisture castables as a top cap material. But do this castable lining actually when the furnace in warm condition, so the moisture is not being absorbed by the dry ramming material, which is at the bottom. And also, whenever you do a different top cap material other than dry top cap material, make sure the metal level is always on the main working lining and it does not come to the level of top cap materials. So coming to the lining tools, lining is normally done either manually or using a pneumatic vibrator or using an electrical vibrator. The first picture shows a pneumatic one. The second one is a Bosch, which is being operated electrically, but manpower has to be engaged. The third picture, actually, the motor, which you can see, the orange one, is an electrical vibrating system. But in general, nowadays, most of the foundries are engaging with Jolter, the pneumatic one. And I'd like to bring the attention of everyone in operating this tool. First, this tool should be used only for compaction, because I have seen in the market people use this actually for de-airing also. They don't do any kind of forking. They just fill the material, introduce the vibrator inside, and then they start the vibration. But this motor is designed only for compaction. So we recommend to fork the material at least 5 minutes for each layer, and then introduce the vibrating motor and then start the vibration. Care which has to be taken while using this vibrating system is should be operated at 6 bar pressure. Pay attention to the air quantity. So use a minimum of 8 mm hose for the airflow between the compressed air and the system. The rammer should be dust free. So because it has a lot of moving parts, so it should be dust free. Adjust the arms according to the form dia. Make sure that the vibration is happening properly with a vibro tachymeter. Use a vibro tachymeter to understand the vibration and make a point actually to note it down, so that actually every time you cross check it, and if any deviation is there in the amount of vibration being transferred, you can check your vibrating this pneumatic vibrator or jolter. In the tapper section, whenever it comes to the tapper section, ensure the distance between the former and plunger are adjusted properly, and run the vibrator for 2 minutes per level, because normally this has been uplifted by the crane. So at each level, actually, you have to do 2 minutes. And when it comes for sidewall, vibrate for 1 minute for each 100 mm thickness, 100 mm distance. Ensure we don't vibrate. So accordingly, set the level and the vibration speed. This is to avoid disturbing the material which has been already compacted. So coming to the advancement and silica lining. So I don't want to put my trade name. So I generally put like ALGT, which is like advanced large grain technology. This is a new grade of silica in the market. It is not exactly new. It's been there for for many years, but still very few customers are carrying a mindset on how this will work. So I take this opportunity to explain the same here and its advantages. Normal grain sizing is 4.5 mm to 6 mm, but this product contains 12 mm on an average in a bag. So there are certain grains which is little bit bigger, but if you consider the average, it will comes like 12 mm particle size, which is about 60 to 100% larger than the maximum grain size of a traditional silica, which I said like 4.5 to 6 mm. What it does, the increased grain sizing reduces the surface area exposed, and this is not only exactly a boron oxide; it is a special binding agent actually, so that the larger grains are kept on hold during the sintering process. So it has a special binding agent. So this new binding agent with the grain sizing gives you better sintering process and helps in attaining a better hot phase. So when it comes to the additional benefits, it has a better packing density is being attained because we had some cases where we remove the foam even without introducing any kind of heat. So we don't normally recommend it, but there was one customer who did it. The idea of sharing this is this product compacts so well so that actually you can remove the foam also. But normally it's not much recommended because it's unsafe. This product has been designed actually for suitable for liquid sintering, and it has, because of the grain sizing and grain distribution we have, it has improved abrasion resistance, especially in areas like taper section or cone sections where you find a lot of elephant foot erosion. So CAD during sintering, let us talk about sintering. Normally people tend to go with kilowatt basis, but we always say that refractory understands only temperature and time. So try to follow the sintering with the thermocouples and not by kilowatt, which is power. So a K-type thermocouple does not cost you much. And when you remove this thermocouple, 1000 degrees Celsius, 100 degrees Celsius, which is the critical area for the sintering of a silica. And this thermocouples can be used on a long time basis if you're not going to damage thermocouples, keeping it for a long time. So when it comes to types of sintering, there are two types of sintering. One is solid sintering and one is liquid sintering. If you talk about solid sintering, everyone does the same operation, like furnace is being charged with the scrap and the sintering is done through the power. So our recommendation is to rise between 80 to 100 degrees Celsius per hour, depending upon the furnace size. Hold at 550 degrees Celsius for 30 minutes, then rise till 900 degrees Celsius and hold for 1 hour. And then you can increase the power, melt the scrap, and take it like 50 degrees Celsius above your tap temperature, which is normally between 1550 to 1600 degrees Celsius, and hold there for 1 to 2 hours, depending upon your size of a furnace. So that cycle is normally used to engage for silica linings, but when it comes for alumina linings, for steel melting applications, we suggest actually to go between 200 to 220 degrees Celsius per hour, and then you can directly shoot out actually like 1600 degrees Celsius and then hold. And in case of larger capacity crucibles, you can hold around 1870, 870 or 900 degrees Celsius for 1 hour. When it comes to liquid sintering, this is one of the best sintering practices, but many people are concerned about engaging this into their operations. But it's very safe if you do it in a proper manner, and it gives a longer lining life for your refractories. We recommend to load actually 1/3 of the clean scrap inside the form with the help of gas torch. Raise the temperature to 1100 degrees Celsius at a rate of 150 degrees Celsius per hour. Hold the furnace for 2 hours. Prime the liquid metal at 1500 degrees Celsius from the other furnace. So thereby you get a clean liquid metal from the other furnace. From that furnace, actually, you can bring into this sintering furnace. And after tapping, switch off the furnace for 15 to 20 minutes. So there's no much turbulence actually because of the power. Then slowly raise the temperature because there'll be a drop in temperature. So slowly raise the temperature to 1550 to 1600 degrees Celsius and hold for 2 hours. as I said before, we recommend this liquid sintering since it gives a clean sintering to your lining with no slag attack to the main working lining or no saturation in the initial lining. So when it comes to advantages and disadvantages of solid sintering, advantages, anytime we can go slow and consistent with the temperature, the refractory will perform consistent, less chances for rapid failure during sintering. But when you talk about disadvantages, high energy use, long downtime, need to use very clean scrap free from oxides and sands, uh, easier to cause bridging. Sometimes actually there's a possibility of losing the form before the molten metal is being introduced, and this lead to exposure of lining to the metal with no pressure. When it comes to advantages and disadvantages of liquid sintering, it's fast, less downtime, less oxides formation, and less oxide actually in contact with the refractory during the sintering. No chances of bridging. Refractory will stay in compression, less energy consumed actually. But when you talk about disadvantages, as I said before, you must be very confident actually, and the process has to be taken with utmost care. So as I said before, use thermocouples during the sintering so that actually you can monitor the temperature. Because there's always a concern actually, which when I go to the customer place, actually, as I said in before, using a thermocouples. So what we recommend is at least to run couple of cycles with the thermocouples, note down the temperature versus kilowatt, and frame a chart, and then try to follow the kilowatt, and have a periodical check actually every 6 months once, or 1 year once, whether whatever you're following is right or wrong with the help of thermocouples. So normally during the sintering, actually we ask to bring the liquid metal as much as to the top, and you can see this is the normal metal level, and during the metal sintering, actually bring it till the top, and at least actually you can do this for 3 to 5 linings, and then you can go down the metal level actually to a normal metal level, so that the lining is sintered properly throughout. So when it comes to sintering parameters, care has to be taken, and I like to talk about that actually here, which is like changes in the charge density and charge makeup. Make sure actually the charge is dense, clean, oil-free, rust-free, no borings. Make sure actually you follow the right cycles with the holes wherever is being recommended. Like I said, for silica, 550 to 600 degrees Celsius or 900 to 1000 degrees Celsius, and then final hole. Minimize the power input as the charge begins to melt. No alloy additions or carbon additions until 75% of the furnace is full. Don't add steel charge until 50% of the molten metal during the sintering heat, which we'll be talking about why it is in the later of the presentation. Make sure actually you have a proper thickness for the form. Normally, we recommend 6 mm is a starting thickness actually, and when the furnace goes bigger, like 10 ton or 12 ton, we go till 8 mm also. So we don't recommend actually 3 mm because the refractory always has to be in compression. A 3 mm form has a high possibility to get cut due to some kind of arcing, and if the former is cut, the refractory is not under compression, and in that area you can see a kind of spall. So we always recommend to have a proper thickness of the form. So coming to common lining problems. So one common lining problem is carbon saturation. If you see this picture, so this is the hot phase, and on the cold phase side, you can see a black spot. If you see the below picture, the same thing. The hot phase on this side, there's a middle portion which is white, and on the cold phase, you can see a black portion. So it is all because of carbon deposition, and carbon deposition starts when the temperature, as the temperature goes near to the coil, it's always less. So below 500 degrees Celsius, the carbon deposition starts, and it has been aided because of presence of rusty scraps and oil in the borings or oil in the scrap. And the moisture is also one more cause for carbon saturation. What happens actually when the carbon saturation happens? As it grows and grows, GLE tripping happens due to earth leaks, and intercoil arcing happens. In case actually if you come across such in your foundry, to understand whether it's carbon or not, you can easily test it in your lab by doing LOA test, that is loss on ignition test. Take this black refractory, put it in your furnace, and take the temperature above 1050 degrees Celsius. The weight difference between the initial charge and the final after 1050, after heating into 1050, that indicates the carbon content. And also the silica turns back into white again. So all the carbon evaporates, goes out actually, and the refractory looks white again. If you see this picture, that indicates the same. So that's an easy check actually, which can be done even by you at your own labs. Coming to the solution, how to eliminate this issue. We need to first ensure a proper installation, that is densification of the lining, and hot face formation, following the right procedures for the sintering. And when it comes actually to the other part, make sure actually that the grout has been dried out, and the other structural components like bottom blocks and top blocks are dried completely, because all these contains moisture. And when the furnace is new, there's a lot of possibilities actually that more amount of moisture is there in the system. So make sure actually a proper dry out cycle is being followed to eliminate all this moisture before the lining is being started. Use only oil-free or rust-free scrap. Don't add carbon until the liquid metal is 50%, or at least actually 1/3 of the level. Follow the right sintering procedure for good hot face formation. As I said before, liquid sintering is preferable. Again, I'm talking about the same. And also one more point I like to add here is I try to avoid adding fine grade carbon. And also, if possible, if you're trying to use oil scraps or oil borings, try to burn out the oil outside externally before it's been introduced inside the furnace. Coming to the erosion part, erosion normally happens because of two reasons. One is chemical and mechanical. Chemical is because of metal chemistry attack and slag chemistry attack. Mechanical is because of mechanical abuse and stirring action. When it comes to erosion, carbon silicon equilibrium plays a major role at a set temperature. In case if the carbon increases in the liquid metal and the silicon percentage decreases at a set temperature range, the reaction towards the silica lining is going to be strong, and the carbon is going to pull out the silica from the main working lining, and it is going to erode the main working lining. So if you see this carbon silicon equilibrium, this is a graph which we normally show to our customers actually about the equilibrium we have to maintain at a set temperature to avoid any kind of attack over the main silica lining and to control the erosion pattern. So this slide talks about the reaction of the initial charge over the silica lining. For an example, if you have a lot of iron oxide reduces the melting point of silica to 217 degrees Celsius. MnO present actually in the metal reduces actually the silica from its melting point actually to a range of 1345 degrees Celsius, because normally silica melts at 1710 degrees Celsius. So try to avoid all these things, and we'll be talking further on this. Also, you can note that carbon silicon content of various ferrous chemistry in this graph, in this slide actually. This will help us to keep a check on the charging practice during the sintering and regular operations. Also keep a watch on the alkali levels. When it increases, it also has a strong effect over the silica working linings. So slag is one reason actually, and understanding a slag is important to minimize the erosion. Slag formed during the melting process, it comes in first contact actually over the refractory. Based on the chemistry, it has an effect over the lining, either in form of erosion or on the form of buildup. Slag is due to iron oxide present in the scrap, impurities in the scrap, like cupola slag, which contains CaO, scrap with the mold sand. We are talking about deslaggers, which is like slag coagulants, also contributes to the erosion, because these slag coagulants contains a lot of elements like MnO, Al2O3, Fe2O3, and other alkalis, which has low melting point, which in turn leads to the oxides, formation of oxides, causing an attack over the lining. So we're coming to understand actually iron oxide, because this one thing which we always talk about actually to our customer whenever, because nowadays with the technologies growing up and this automatic shaking system coming up into the play for charging the furnaces, these shaker systems are so strong enough, and it's so strong enough actually that it segregates your rust and the scrap. So because of the vibration, whenever you try to charge the furnace, the iron oxide enters the furnace first, along with the scrap. Uh, it gets deposited on the floor, on the side walls of the linings, and the melting operation starts. The liquid metal gets saturated with the iron oxide, and it generates a lot of high fluid slag, which easily enters into a working lining. And when the lining is new and fresh, it has high chances actually, because the lining is like a honeycomb, so it tries to suck up the oxides, and it saturates very fast. So what happens is actually this saturation lowers the melting point of silica and erodes the lining pretty fast. To overcome this, we recommend the arrangement as shown in the picture. This will help you to collect the iron oxide before getting inside the furnace. So you can create a mesh so that actually when this shaking system is trying to push a scrap inside the furnace, all the rust has been collected actually through the sheave before it is entering into the furnace. So coming to the charging practice again, we recommend to charge actually the returns first, followed by pig iron and steel. Any additives such as carbon, Mn should be added only after 1/3 of the molten metal is formed, or at least 50%. Actually, 50% recommendation, or otherwise at least 1/3. Try to have different sizes of charge to avoid bridging, because once bridging happens, it's very hard actually for the upper scrap to get in, and then your bottom side actually metal is going to get superheated, paying for the refractory to run out. Avoid zinc coated scraps, oil scrap, and sand coated scraps. When adding actually in the freeboard area, that is in the top block area, please take care actually while adding it. Make sure actually the charge is getting in, to avoid any kind of bridging or superheating at the bottom. In case actually if you have heel metal, reduce the power and charge the furnace back as soon as possible. So to attack an elephant foot erosion, normally with my 14 years of experience, actually, I have seen a straight form being given by the OEMs as a regular practice, and then we convert it into a tapper section. But even the tapper section was not helping out actually for on a longer run to avoid elephant foot erosion. So the later on actually it has been found actually that this tapper helps a lot actually. Because this helps you to easily install the refractory with a proper densification, and it is helping you out actually in the long run for the elephant foot erosion. So this is one preferred tapper when you design a form to avoid actually any elephant foot erosion. So coming to finning. Finning is metal penetration in the lining. It's because of cracking. Cracking can be either horizontal, vertical, or random. When we talk about horizontal, these are hard to seal, and it's majorly because of lamination or lining gets hung up. Lamination is related to installation related. For an example, you do a manual ramming, you fork it, do a compaction, and then before forking, if you're going to add this refractory, there's always a lamination, and it can be easily identified when you break the lining, because in the complete circle of the furnace or circumference of the furnace, the metal will be like a washer sitting in. So it's called as lamination. When it comes to lining hang up, it's mainly because, as I said, actually in the initial stage, when we were discussing about grout, the grout has to be as smooth as possible. If the grout is not smooth, and if you're going to do a lot of repairs to your grout, as I said, actually when we are discussing about grout, the grout has to be smooth as possible. So we have to minimize the number of repairs we are doing to the grout. The reason behind this, as long as actually you're going to increase the amount of repairs to the grout is not going to be smooth. And when the lining is under hot condition, when you're going to heat up the lining, it expands. And when you're going to cool it down, it does not contract the same fashion. And wherever there's a projection in the grout, these projections will not allow the grout to settle down smoothly, and it creates a horizontal cracks, which is very hard to seal up, and it has a high possibility of metal gets penetrated to those cracks. So we call normally it is because of structural related. So we need to take care of it. Vertical cracks, thermal cracks, these are very easy to seal up if you're going to follow a proper cold start procedure. Random cracks, mechanical abuse, it's because of the way we charge the furnace, or any unbalancing in your hydraulics or your structural things. So otherwise random cracks will not happen. And random cracks, again, it's very hard to seal up, and it can also lead to a metal penetration issues. So as I said, this is what I said earlier. So coming to this has not been still again widely followed, but still we keep recommending our customers, and we try to educate our customers how important a rapid cooling of is important actually for lining. So this will help to minimize the large cracks and create lot of smaller cracks, as I shown in the picture. This will easily seal up if you are going to follow a proper cold start procedure recommended by the refractory supplier with the help of thermocouples. Slow cooling will always have few cracks, but a wider cracks, and this will be hard to seal up. So traditionally, we are following slow cooling. We just either, there are people actually who put charge also inside the furnace, which is not recommended. If you want to do a slow cooling, just empty the liquid metal out, put a blanket on the top, and let it cool, rather than putting any charge or any scrap inside the furnace. So this will help you a lot. So rapid cooling, this is the way we normally recommend. What we say is, if you see the circles here, this shows actually the spout area, and this is the working lining with the top cap. So after the last heat, normally you keep the furnace tilted down a little bit to have this metal and slag coming on one side so that it will be easy for you to clean. But slag sits here also in these circles. So try to break those slags, and so that actually the lining can settle down during the contraction with no hindrance. If the slag is going to be here, it is going to be tying up your working lining with the spout, and the lining will not contract smoothly. And because of that pressure, you can have any kind of horizontal cracks wherever the stress is created. So break those areas and then put a compressed air on fan on one side. So air flows on one side and goes on the other side. Again, coming to cold start procedure. So now you have done a rapid cooling or a slow cooling, but when the furnace is supposed to be restarted again, we need to follow a proper cold start procedure. Cold start procedure is one of the area where more attention is required for the better lining life. Normally, every foundryman or every foundry people follow a slow start after a cool down of the furnace, which is not required. Raise the power so that the charge can be red hot. It can be fast. You can raise it as fast as possible, but make sure the charge is red dot condition. So the lining is red dot in condition, but there should be a care given that the metal should not melt. The charge and the lining should be in red dot condition. At that stage, hold for 1 to 2 hours, depending upon the size of the furnace. During this hold, refractory expands and gets sealed actually. So this is the important stage, because you need to allow the refractory to expand. If you're going to do a slow start, you think actually you're giving a slow start, but you're not giving a holding wherever is required, and then you're trying to melt, and this will be allowing the metal to penetrate to whatever cracks were being developed actually during the cooling process. So holding is important. Hold for 1 or 2 hours at red dot condition for the refractory to expand and seal up, to avoid any kind of finning happening. There are certain people actually who does this to minimize the cracking. They always keep the torch on, so they put a burner and they keep the lining hot in condition. They keep the furnace closed as whenever possible. Minimize the tapping and charging time. As I said, post cooling is what we recommend, and cold start procedure after extended downtime. Coming to superheating. So coming to superheating, superheating can be because of bridging or trapped metal within the refractory cross section, or superheating of the metal bath because of the poor temperature control. So as I said before, if improper charge or scrap is done actually during the charging practice, it will the huge scrap actually will not allow the smaller scraps to get in, and there'll be a lot of hangups. And we try to miss it actually, where the bottom metal will be getting already the power, and it will start to melt. And since actually we are not sure about the melting operation and the charge is not getting in, or there's no contact between the charge and the scrap, this leads to superheating, and the metal will run out actually wherever the silica gets melted. We always say that actually proper slagging is must. So deslagging, do the deslagging properly, and then try to charge the furnace and make sure actually there's a contact between the liquid metal and the scrap always, so that we can avoid superheating. So these are some pictures. Because silica melts, you can see through this picture actually we can't see any kind of grains. It looks glassy, and it's completely like one monolithic structure actually. So spalling, it's because of spalling. Normally, it's like a piece of refractory falling off from the hot face or in the bottom. It can be either because of steam spalling or mechanical spalling or differential expansion or pinch or thermal. Steam is mainly due to steam generation. It's because of the moisture. As I said before, uh, the moisture in the system has to be removed properly before the working lining is done. So that's the reason we recommend you to go follow the GLD values or the moisture meter values to ensure the complete moisture has been removed from the system. Normally, it's very less seen in coreless furnaces, but it is largely seen in ladles and pressure pores and tun dishes, where we engage with castables. So that is one thing. Mechanical spalling is because of mechanical abuse. When it comes to differential spanning, it's because of saturation. So when we talk about saturation, as I said earlier, uh, like to avoid saturation, we talked about going with liquid sintering. We talked about a proper selection of refractories and proper sintering practices to shut the porosity as much as possible. Because the lining is like a honeycomb, okay, or like a sponge. So it tries to pull out all the slag or impurities along with the metal into it actually, and keep it along with that. So when the power is given, power is fed more and more for the melting operations, this whatever saturation happened in the lining also travels towards the coil, leading to GLDs. So it can be because of metallic and non-metallic. And as I said, actually, it can be because of low density and chemical attack. So make sure actually you properly sinter the furnace, uh, properly line the furnace, and um, this can avoid saturation. Pin spalling is again because of refractory compression. So for an example, many people would have seen this in the bottom of the furnace. For an example, when the bottom of the form is not completely in contact with the refractory, what happens is, if there's a bend or there's a curve or like concave or something, so refractory tries to expand actually to that level, and then once the centering operation is completely done, then you can see a small popped up refractory at the bottom. So normally we suggest actually the customers to ensure the bottom is completely flat and it is completely sitting over the refractory 100% to avoid these kind of pin spallings. And thermal spalling is because of rapid temperature change during the operation. So these are some pictures actually which shows about spalling. So in this picture you can see during the rapid cooling operations actually they pointed out the air towards the working lining, and then because of that actually, because of sudden temperature differences, those spalling happen. And here you can see a pin spalling at the bottom. This is, as I said, actually, this happens majorly. These are like steam spallings, which happens majorly in furnaces like channel furnaces or pressure cookers or condensers. Saturation, which we already discussed actually, because of low density and molten metal exposure without hot phase formation and chemical attack. And these are pictures of saturation, how a saturated lining looks. So buildup, it's because of the oxide formation, metallic oxides adhering to the furnace working lining. It can be oxidation of molten metal and contaminations actually from the charge into the furnace. So this will reduce the volume of your metal, and then because of which actually the power rating is also increased, and then you tend to break the lining. So in a nutshell, I suggest actually for a better refractory lining life in your furnaces, inspect the furnace completely, both mechanically and electrically, and ensure the furnace is ready for lining. Select the right refractory for your operation, depending upon what you melt. Normally for silica, for iron melting operations, nothing much. Normally it is only silica because that is a cost-effective solution. But the boron oxide percentage can be varied from 0.6 to 1%, depending upon your operation. And again, in case if the furnace is going to be put into a lot of thermal cycling, then fused silica is one of the solution which you can look into it. And there are a lot of grades in fused silica also, ranging from 15% to 40%. So depending upon your cost viability, we can choose fused silica. That comes under selection of right refractories for your operation. Ensure lining tools are checked and ready to use. Follow the lining and sintering procedure recommended by the refractory manufacturer and supplier. Charge the furnace with the right charge, as we discussed, like returns first and pig iron and steel next, to avoid any initial saturation and erosion happening to the lining. After the initial sintering, try at least to complete 5 heats with no stop to the furnace, because there are people actually who shut down the furnace immediately because of the production capacities, which is not recommended because your hot phase formation is not still yet completely formed matured enough. So try to at least take 5 heats before you shut down a furnace. Avoid dirty charge and oil-free charge during the regular operations. Normally, whenever you shut down and restart it, ensure actually the joint between the spout and the working lining is good enough. If you find any kind of small cracks or something, you can just clean it up, make a V notch, and put the plastic refractory again and seal it up to avoid any metal penetration happening through that particular joint. Follow right cold start procedure after cooling down the furnace to seal up all the cracks and to avoid finning. After the last step, when the furnace is going to be put into cool down, as I said before, try to knock down the slag sticking over the joint area of the spout and the working lining, so the lining contracts smoothly with no hindrance. Try to make the top cap only to the level of the top block and melt below the top block level. Because what happens is, if you're going to make any kind of heap, this is not going to sustain for a long period of time. If you're going to make heap actually with sodium silicate, it cracks easily, and even this can lead you to unsafe operations. And since, as I said, actually the sodium silicate does not have the strength, and it's always stays there as a cracked one. It also get into your liquid metal while tilting the furnace, and it also can create inclusions actually to your castings. To avoid this, try to choose a proper top cap refractory and try to maintain to the top block level. Maintain proper records of complete lining procedure, sintering, and alloys melted. This will help us to understand the areas of improvement and to do the analysis in case of any lining issues. So maintain a proper record for inspecting in case of any issues. We also recommend actually our customers to keep the spent samples, that is after 400 heats or 500 heats, for an example. You try to store that sample lining sample from the side walls on the bottom, at least for 1 or 2 linings, till 2 or 3 linings has been completed in the same furnace. This will give an idea of how the sintering is happening, how the semi-sintered zone is there, how the cold phase zone is there. So based upon that, actually, we can take a call whether we can extend the lining or not. So we can collectively work together to increase the lining performance based upon these things. So always try to hold the lining samples, and then especially when an issue is happening, just collect that sample on that particular area where you have noted the issue for us to come and inspect the thing. Because without inspecting the samples, it will be very hard for any refractory supplier or a manufacturer to give any kind of recommendations or suggestions on why it has been happened actually. And also, in case if we need to check that samples, we can also do a check on the samples actually by sending it to our laboratories to understand why that issue has really happened. So make sure actually you hold the samples for inspection, and periodically call us for training, your team at your facility, and we'll be happy to do that. Because as I said initially, these things comes like refreshing things actually for the people. So and there'll be some changes in your team also. So for the new team, it will be a good learning, and for the existing team, it will be a refreshing one. So periodically call us for the training at your facility, so that before the training is being started, we can go through your foundry, we can see your operations, and based upon that, actually, we can give you inputs during the training. So that's it from my side. Thanks for listening to me, and we'll be happy to take up your queries. And I have my mail ID and my contact number here. If you want to write down or call me over the phone, you are always welcome.
Yeah, thanks, Raj, for a very detailed presentation, giving the best practices to be followed to achieve optimum life in Coreless Induction Furnaces. So with that, gentlemen, we are open for questions. So you can either unmute yourselves and ask the question, or you can put it in the chat box, and Mr. Rajmohan will be more than happy to answer your questions, please.
I'm Govind here from Bangalore.
Yes, sir.
Yes, sir.
Which furnace size you recommend for going in for that increased grain size, 12 millimeter grain size?
So if you have a lining thickness of 2.5 inches and above.
2.5 inches and above lining thickness. Okay.
Yeah.
Okay.
This product can be used, sir.
Okay. Then one more thing you didn't mention in your this one, a lot of people melt above the coil level.
Yes, sir.
For the lining life reduces, and then efficiency of furnace also reduces. So for what are your comments on that?
So that's true, sir. As you rightly said, we don't recommend actually to melt anything above the coil level. Because
I would like you to put this in the presentation so that people stop doing that practice. I find it everywhere.
Surely, sir. Surely, sir. I'll take your advice. I'll do it in my next presentation.
Raj, if you have any photos about the extended top cap, if required, you can show.
No, see, like what Govind sir is saying, actually, first of all, it is not recommended
Correct.
melt anything above the coil level. Okay,
Yeah.
because you are going to lose the efficiency of the furnace.
See,
Okay.
many foundries also increase the line of the lining itself in the top to increase the melt capacity.
Yeah,
Correct.
that's
not
what
only they lose the efficiency of the furnace, but also they create other problems.
Yes, sir. Like what Vignesh is saying right now is, what happens is there are certain people who can't avoid it because their operation is set in such way. Okay. But what we are trying to do is we are trying to make it at least a safe operation for those people who want to really melt above the coil level. Okay. So normally, rather than making it as a heap, for an example, you make a heap with a sodium silicate or any kind of refractory. But rather than doing it, we have a product actually which is called a stuff load, and we make top blocks out of this product, and we use this product actually to extend the top block level. For an example, if you want 3 inches to be extended or 6 inches to be extended, so we do it above the top block, and then we try to bring the dry ramming mass till that level, so that in that case, at least actually there will be a kind of safe operation.
No, I'm not talking about safety. I'm also talking about the the furnace efficiency, the power.
Yeah, that's true.
That is true, sir.
That's true. That's what I'm saying. I don't suggest the customer to do that above the top block level, but in case actually if they can't avoid, I'll try to at least save that actually by using these products.
Okay, I think you can mention that. It will be interesting.
Surely, sir. Surely, sir.
Then one more question, nothing to do with refractory. This is for some other thinking that I have got in my mind. Since you are a ceramic master's degree holder, I'm just asking you this question. I don't know whether we have the right answer. Is it possible to change the phase changes of silica sand before we use it?
Phase changes of silica sand actually before we use it.
Yeah.
Which you are talking about?
It is a hypothetical question, nothing to do with refractory.
No, you are talking about silica sand or silica this refractory you're talking about?
Sand.
No, sir. I don't think so, but I can put this actually to my other colleagues. I can get back to you.
Okay. I'm thinking of something else. That's why I just asked you this question.
No.
If you can answer me that, it will be later on. It will be great. Thank you.
I'll just check and get back to you, sir.
Thank you very much.
Thank you, sir.
Raj, there is a question in the chat box. Mr. Mathiazhagan from SNAM. What should be the boric acid addition percentage for high temperature, 1580 to 1600?
Boric acid.
We should say boron oxide then.
Boron oxide for that temperature range actually will be like 0.8, 0.6 to 0.8 is our normal recommendation. I can 1 minute, give it some time. I can check with the boric acid versus boron oxide ranges if at all he wants boric acid.
Sir, Mr. Mathiazhagan, if you want, you can unmute yourself and ask if anything is specific, because like we mentioned in the presentation, boron oxide is better recommended for better lining life. And so for that kind of material, the temperature that you're asking for, 0.6 or 0.8 will be the optimum boron oxide percentage to add for this temperature, sir.
Sir, actually, I want to know that actually we are using silica ramming mass with boric acid percentage of 1.4.
Okay.
And our maximum temperature will be 1600.
Okay.
So what problem I am facing is after the 45th heat, that erosion is happening very highly, sir, in our furnace.
True, sir. Actually, because I know your complete operation and we are working on certain trials at your end.
Yes,
okay. You have a different scenario. Your furnace on the top has a buildup. On the furnace on the metal level, below the metal level, you have erosion.
Yes, sir. Yes, sir. Yes.
So we suggested actually to go with chrome-based silica, and with a chrome-containing silica, we found actually there's a lot of advantages in terms of erosion, but still it is not consistent. Okay. And we are working on that, and we'll be coming up with a solution. But in general, to talk about boric acid versus boron oxide, we always recommend boron oxide mixes, because boric acid is hygroscopic in nature. You know that it has H3BO3 and boron oxide is B2O3. So boric acid, normally what people does it actually in the past, I think a lot of seniors are here and they can talk about actually, they put this boric acid, they mix the boric acid on the shop floor and they put it for preheating around 80-90 degrees Celsius or 100 degrees Celsius.
Yes.
But still there's a chemical moisture which is involved. This chemical moisture will not escape. This chemical moisture will escape only at 400 or 500 degrees Celsius. Okay. That means actually when the lining is inside the furnace. Okay. And this moisture will create a porosity on the hot face.
Okay.
So in case of boron oxide, this is much all these chemical moisture have been already eliminated. Okay. So your hot face formation is much better compared to your boric acid linings.
Okay, sir.
So that's the reason actually we were able to be successful or show some kind of improvement in your operations also.
Yes.
Okay.
Yes.
So normally that's the reason actually, as I said before, when the technology is changing, people are moving towards boron oxide. a lot these days because of seeing the performances. And also there was one study which made in one of the well-known foundry in Coimbatore, where this boric acid also leads to a lot of maintenance towards your coil, because your moisture escapes and gets settled in your coils. Okay. And this creates arcing between your coils because it creates a reaction with the copper coils. So that is one study which we made. So we always recommend boron oxide for your mixes.
Sure, sir. Thank you.
Thank you.
Thank you, sir.
Sir, there is one more question from Mr. Suhas. For what time we have to hold the furnace in red hot condition, having 1.5 metric ton capacity when cold starting furnace?
At least an hour is normally recommended for 1.5 ton furnaces. So that's what I said. So rather than spending the time on a slow start, you can go a little bit faster and make the charge underlining red hot and then hold for 1 hour at that point of time. This will allow the refractory to expand and seal up.
I think LavaCast has raised their hand.
Yeah.
Sir, you want to? Yeah.
Yes, sir. Good evening. Good evening, sir.
Good evening, sir.
Actually, my question is that as per technical, when we break the lining, we get 3 layer of lining, like sintered, semi-sintered, and powder form.
Yes, sir.
But right now we are not getting powder form in lining when we break the lining.
Sir, actually, you mean to say that, see, there are two things. One is powder form is clearly visible. And other way is, for an example, if you rub it out, if you take that sample and if you rub the coal face, even if you can find a powdery layer coming off, even that is good. Because in my own silica, the new technology of silica, which we are talking about, large grain silica, it's not that kind of easily you can find a powdery coal face. But the metal will be powdery. If you rub it, actually it will come off. So whether you are able to see that in your samples or not.
Yeah, when we break the lining and we check all lining has sintered. Is there any cause and relation between the grouting and lining?
Sir, it depends. That's what I said actually in my last summary, that it will be good enough actually if you can share me a picture, or if you can that will be helping me to understand how the lining looks, and based upon that I can give you an input actually on that.
Okay.
You have my mail ID.
Raj, I think you can put it up again.
Okay, sir.
You can put
Okay,
that screen
sir.
up
We
again.
try to share. If you have image, then I will
Yeah.
share.
Yeah.
You can see my screen.
You can leave it
So
here, Raj. Yeah.
you can send a WhatsApp to me, or you can send an email to me. So I can call you back actually with the answer to your question.
Okay, okay, sir. Okay, sir. Sure.
Thank you, sir.
Sir Rajmohan, sir.
Yes, sir.
I am Chandrasekhar, Industrial Caste.
Tell me, sir, how are you, sir?
I'm fine. And I have one question, sir. I think you aware about our problems, sir.
Yes, sir.
In our furnace, if we use normal boric acid ramming mass, and we use our boron oxide ramming mass also. So below the top block level, always we are having between the coil to top block area, we are having issues in after 200 heats or 300 heats like that. We are not doing any batching. So this is our major issue in all linings. What will be the cause of that?
Sir, this is one thing which is coming up commonly in all the foundries, because your cooling pattern differs between the top block, where the top block area is, and where the cooling coils are there. Okay. So see, that's what I said actually. If you're going with the rapid cooling procedures, you can avoid this, because you will be letting a fan inside or a compressor inside, so that there's a uniformity in your cooling cycle.
Okay.
In case of slow cooling, this is one thing which is happening on a regular pattern actually in many of the foundries, where the top block does not have any cooling effect, and the coil area has a cooling effect, and because of this differential and cooling effect, the crack forms in that area.
Okay.
Might
That-
be we can come down and we can support you actually to see one time how a rapid cooling helps you out.
Or otherwise, when we stop the furnace, we can reduce the coil water flow. Is it works well?
That part we have to discuss with the OEM also, sir. But to some extent, yes, it has helped actually. But with the recommendation of OEM, we can do that.
Okay. So rapid cooling means we have to do the forced air cooling, huh?
Yes, sir. Yes, sir.
Okay,
Yes, sir.
with the compressor air or some fan.
Fan, yeah.
Okay, okay. Okay, sir. Thank you.
Thank you.
Raj, there is one question from Autocast in the chat box. Could you please suggest the lining material for 6 metric ton mains frequency furnace for melting up to 1550 degrees Celsius?
Same, what type of alloys, Vicky?
I'm not too sure, but it is a main frequency furnace, not medium.
But still, alloys.
Sir, can you unmute yourself and ask the question, sir? So
I think they
team
should be for iron. They'll be again using the same product, no?
Silver.
What? Yeah, no, not silica. I'm talking about silica. Okay.
Right.
So for iron melting application, silica is the only option, cost-effective option.
Right.
But might be I think actually the life might be varying because of the main frequencies and the flux reaction towards the lining and the charge.
Any further questions, gentlemen? Like I said, you can unmute yourself or you can type it out in the chat box. And like many of you are asking in the chat box, we will be uploading this recording in YouTube. So it will be of useful to you to have a reference point later on also. So if there are no further questions, I think we can move on to the vote of thanks. Thank you, Raj, once again. So
thank you, Vicky.
Gentlemen, we have had a very interesting webinar today on the topic best practices to increase refractory life in coreless induction furnaces. It was a very pictorial and well-made presentation. So we'd like to thank our speaker for the day, Mr. Rajmohan Mathiazhagan, National Head, Allied Refractory Products India Private Limited, for taking time off his schedule and making us rich with knowledge. And we also thank all the members who joined us for this talk. I'm sure you had a wonderful learning experience. And thank you for joining us on time and being such a wonderful audience. We from the Chennai chapter will be conducting many such interesting programs, both physically and virtually. And we'll be sharing information on the same with you soon. Looking forward to seeing you all in our upcoming programs. Thank you so much. Thanks a lot, Raj. Thank you.
Thank you. Thanks to all.
Thank you so much.
Joining.
Thank you.